Hello students, in today's class we will be discussing about the third type of AC circuit, that is circuit containing inductance, capacitance and resistance. So a circuit is there which has all the three factors. Those are inductance, capacitance and a resistance in series combination, which is applied to a alternating voltage. So this alternating voltage is V, which is equals to V naught sine omega t. So this alternating voltage is applied to inductance, capacitance and a resistance which is connected in series, and the same current I flows in the three factors over here. Three devices over here. Okay, the same current flows in a series combination. Now the voltage across inductance is VL. Potential difference across inductance is VL. Potential difference across capacitance is VC, and potential difference across resistance is VR. So along with that, simultaneously I will draw the phasor diagram of this as well. Okay, so over here I draw the phasor diagram. So I is the current in this circuit at any time, and VL, VC and VR are the potential difference across L, C and R. So VL is the potential difference across inductance, VC across capacitance and VR across resistance. Now from the previous derivation of inductance, VL was IXL. Potential difference is equals to current into resistance. So this XL is known as inductive reactance. Okay, this is inductive reactance. Now VC was IXC. XC was capacitive reactance, and VR is IR, which is potential difference across our resistance. By Ohm's law is I into R. R is the resistance, which is here. Now from the individual derivation of all these things which we have done in the previous chapter, what we know is VR, that is this potential. If a current I flows in the potential across this VR, then VR is in phase with I. That means the angle between V and I across R is same in this circuit, that is our resistance circuit. So in this one it is in phase with I. Now VC, we'll draw the vector diagram also. Now what we can see in the VL circuit is, when there is an inductor connected to an voltage, the current flowing through an inductor will be out of phase. That means the phase will not be same. The VL will lead I by pi by 2 or 90 degree. So over here I lags by 90 degree, and in a VC circuit I will lead by 90 degree. Okay, so these three things you need to remember. These are from the previous derivations. So according to this we can draw the diagram. So first of all we will consider vector I. Okay, consider I vector along x-axis. Now for the resistance, okay, for the resistance, VR is in phase with I. That means VR will be in same direction as that of I. So VR will be in the same direction as that of I. So this line represents VR. Let this point over here be A and this point be O. Okay, I and VR will be in the same phase. That means the angle between VR and I is 0. Now the second thing, that is VC. VC over here I leads by 90 degree. That means VC lags the current by 90 degree. So if it lags current by 90 degree, it will be 90 degree behind the current. If current is this side, then the VC will be 90 degree behind this. This line represents VC or vector VC. This point over here is C. Now the third one, that is VL. Over here, I lags by 90 degree. That means VL will lead by 90 degree. So I is lagging by 90 degrees, so it will be 90 degree towards this side. This side will be the VL. Let this point over here be B. Now, for resistance, voltage and current will be in the same phase, so it will be in the same line. For capacitance, voltage lags by 90 degrees, so it will be 90 degree behind. And over here, voltage leads by 90 degree. For inductance, so it will be 90 degree forward. So these are the four vectors. First vector is I, that is current. Another vector is VR, another is VC, and another is VL. We can represent it this way. So angle over here is difference is 90 degree. Over here it is also 90 degree. Now over here what you have to do is, this is for individual elements or individual factors over here. But what happens if, now what you have to do is, we have to actually find the total voltage. Okay, total voltage across these three vectors. Okay, that is VL, VR and VC. So we need to find a total or resultant V. Okay, you have to find V. So our main purpose over here in this derivation is to find V, that is the voltage. Okay, so now look at this diagram. From the diagram itself we can find V. Now what you can see over here is VL and VC are in opposite direction. Okay, they are exactly opposite in direction. Suppose if VL is greater than VC, obviously from this what we can see is the angle of VL, that is VL is leading than VC. Okay, VL is leading VC by 180 degree. So obviously over here VL is greater than VC. So if VL is greater than VC, then these two are vectors. So when we add two vectors, we see which one is leading. So ultimately, if this is greater than this vector, the resultant vector of these two vectors will be in this particular direction. The resultant vector of VL and VC will be in this particular direction, that is in this direction, but it will be shorter than VL and VC. Okay, so this vector is VL. Over here it is a shorter vector, that is a resultant of VC and VL. So resultant of VC and VL, if one is greater, one is smaller, opposite in direction, then the resultant will be VL minus VC. So the shorter vector over here is actually VL minus VC. Okay, this point. So let this point be D. Now this is the resultant of VL and VC. Now the resultant, that is towards this direction. Now there are two vectors left. One is vector OD and other one is vector OA. So if they are in this two direction, now from the vector law of triangle or the parallelogram, the resultant vector will be towards its diagonal. Okay, the resultant vector will be towards the diagonal of vector OD and vector OA. So vector V will be along this side. So let this point over here be F. Okay, now this V represents the resultant vector of VL, VC and VR. Now we have to find V. Okay, so if this is a diagonal of this two sides of a parallelogram, so let us draw the parallelogram as well. Now according to parallelogram, this side will also be equal to this side, which is VL minus VC, and this side will be equal, that is VR and VR. Now the derivation part comes over here. That is, if you consider this triangle, okay, to find V, okay, our main purpose is to find the ultimate voltage, that is potential difference, that is V. Now to find V, if this is a right angle triangle, then this is hypotenuse. So hypotenuse square is equals to base square. Base is VR plus perpendicular square. Perpendicular is VL minus VC square. Let this angle over here be phi. Okay, now this part only we will take further. So this diagram over here is known as phasor diagram. It's given in the book also. So you have to understand each and every symbol and each and every vector over here carefully. Okay, now V square is equals to VR square plus VL minus VC square. Now in place of VR, what we can write is IR square plus, in place of VL was IXL minus, in place of VC it was IXC square. Now taking I square common, what remains inside is R square plus XL minus XC square. Okay, I square is common. Now I square is equals to, okay, if you take I square and rest of the thing in the other side, then it becomes V square divided by R square plus XL minus XC square. Now if you remove this square, there will be root over here. Okay, so if you take this thing out of the root, it becomes V divided by under root R square plus XL minus XC square. I hope this is clear. This is after removing the square, it becomes a root. V square will be out of the root by just writing V, and rest this part will be under root itself. Now if you compare this equation, this is I is equals to V by R. Okay, this, if you compare this equation with the equation of Ohm's law, this is the equation of Ohm's law. So I is I, V is the potential difference, and R over here is this part. This part is represented by, okay, this part is represented by Z. Okay, Z. This Z is known as impedance. Okay, this is the impedance of a circuit, which is actually the resistance of a LCR series circuit. So Z is equals to under root R square plus XL minus XC square. Okay, this is Z. Now let us put the value of XL and XC. R square plus XL is omega L, XC is 1 by omega C square. Okay, this is your Z. Okay, now in this phasor diagram, what we know is V leads the current by phase angle of phi. Okay, this V, ultimate V, leads the current. Current is I this side and V is this side. So V leads the current. If anything is towards the anti-clockwise direction, it is leading. If towards clockwise direction, it is lagging. So V leads I by the angle of phi. So let us find this phi. So in order to find this phi, we will consider tan theta. Tan phi is equals to perpendicular divided by base. Perpendicular is VL by VC, VL minus VC, base is VR. By putting the value of VL is omega L minus VC is 1 by omega C. Oh, sorry. This is the value of XL. So I is also there, okay? Okay, I is also there. I am rewriting this. Okay, VL is IXL minus VC is IXC divided by VR is IR. Okay, I'll continue in the other side. So tan phi is equals to, if you take I common, okay, from the previous equation, if you take I common, then you are left with 1 minus XL minus XC divided by R. So in place of XL, I can write omega L minus 1 by omega C divided by R. This is tan phi. Now there will be different situation if you consider this formula over here. Okay, the phase will be in 3 different conditions. There are 3 different conditions. First one is when omega L is greater than 1 by omega C. When omega L is greater than 1 by omega C, what happens to this equation? If this part is greater, then tan phi will be positive. Okay, tan phi will be positive. In this case, when tan phi is positive, look over here, if this phi is positive, then the voltage V leads the current I. Okay, leads the current I. So V leads I by the phase angle of phi. Second condition, omega L less than 1 by omega C. If this is the second condition, then your tan phi will be negative, then V lags behind current I. Okay, V will lag behind. Third situation, this is a very important situation. VL is equals to 1 by omega L is equals to 1 by omega C. If this two part becomes equal, tan phi becomes 0. So when tan phi becomes 0, when this angle becomes 0, V and I will be along the same direction. So it means that the phase of V and I will be in same phase. Same direction means same phase. So now this condition is very important, because with this condition we can find the electrical resonance. Okay, electrical resonance. This is the condition for electrical resonance. Electrical resonance. So when omega L is equals to omega C, then what happens to Z? The equation of Z which we have derived was R square plus omega L minus 1 by omega C. So if this part becomes equal, if omega L minus omega C becomes equal, this part will be 0. So we are left with under root R square, which is R only. So Z will be equals to R. This is also the minimum value of R. This is the minimum value of R. Z cannot go below this particular value. This is the case of electrical resonance, and the circuit is totally a resistive circuit. Only the resistance matter in this circuit, whereas this inductance and capacitance will not matter at the end. This is the condition for resonance. So condition for resonance is omega L is equals to 1 by omega C, or XL is equals to XC. Okay, now I've just written that omega L is equals to 1 by omega C. Now from here, if you cross multiply this, if you take omega over here and L down, then we can write it as omega square is equals to 1 by L C. Okay, so omega is equals to under root 1 by L C, or is equals to 1 will be out of the root, so it will be under root LC. So this is the value of omega for electrical resonance. Now we also know that omega is equals to 2 by F. This is from the equation of frequency of applied voltage. So from here, F is equals to omega by 2 pi. Okay, from your omega, from this equation, F is equals to omega by 2 pi. Now if you put the value of omega over here, what we get is, we get 1 by 2 pi under root LC. This part is also is equals to F naught. Okay, this is F naught. This is the F naught is known as the natural frequency of the circuit when the resistance is 0 or very, very small. Please note it down. Okay, thus the condition of resonance is that the frequency of the applied voltage should be equal to the natural frequency of the circuit when the resistance of the circuit is small or 0. Now with this, there are a few topics in the book which is not required, such as just after this topic there is an impedance triangle. If you see that is not required. Okay, impedance triangle is not required. So we'll continue with another topic that is resonant circuits. Okay, resonant circuit. Please to check at your book. After a few pages, you will find this topic, resonant circuit. I'm continuing with this topic itself because the condition is this only. For resonance, this is the condition. So resonant circuit is actually nothing else but it is the LCR circuit. This LCR series circuit is also known as resonant circuit. And the condition for resonance is this one, that is XL is equals to XC. That means the inductive capacitance and inductive reactance should be equal. That will be the condition for resonance. Now with this equation over here, with this equation of frequency, we will draw the graph. Okay, the first graph will be of I versus F. I versus F, that is current versus frequency. So for when the frequency is F0, when the frequency of the circuit becomes equals to the natural frequency, that is the F0, at that point current will be maximum. Okay, remember that the current will be maximum. So for graph for that will be, F0 in x-axis, I will be in y-axis. If you draw a graph, you will get a graph like this. Okay, this point where the frequency is maximum, this point is your F0. Okay, this point is F0. This part is the I max or maximum current. Now another graph will be of graph of frequency versus graph of impedance or the resistance of this LCR circuit. So graph will be like this. This point is F0. Now from this graph, what we can see is this is the graph of resistance, this is the graph of current. So when current is maximum, resistance is minimum. Okay, that is what you need to understand from this graph. So this graph is important, and this resonant circuit part is also important, which is actually the LCR series circuit only. Okay, this condition you need to remember, and this equation of frequency is also important. So in the next class I will be doing power in AC circuit, and by 2 classes we will be able to finish this chapter also. Okay, that's much for today. Thank you.